Hello and welcome back to Data Science Castnet. Today I thought it would be fun to take a look at a paper that I've been digging into over the last couple of days and see what insights we can draw from it and then play with some of those insights in code. So let's dive into the paper. No, something doesn't feel right. Hang on. Nope. Maybe. Yeah, perfect. All right, now we're ready to dive in. So this paper is called Elucidating the Design Space of Diffusion-Based Generative Models. And the kind of objective that it comes in to solve is that we've seen these score-based, diffusion models just taking off. Everyone and their dog is training diffusion models on all sorts of different problems. And there's many different kind of formulations, many different ways of framing the problem. And so it's getting a bit hard to keep track of what's going on, and it can be quite hard to compare between different variants. And so what this paper is aiming to do, these folks at NVIDIA have come together and tried to find a sort of unified framework within which they can understand the different variants. And then from that, they're able to draw some really neat insights into different parts of this framework. So they're able to separate it out. So that's their goal. They seek to remedy the situation by presenting a design space that separates the design choices. And then in doing so, they can then iterate and refine the different choices kind of almost independently. And this improvement gives, new extra good performance, and we'll see how those all come together. This introduction just goes into a bit of background, linking some of the key papers that have led up to this recent surge in popularity, right? There's denoising, diffusion, probabilistic models, and so on. Their sort of key claim here is that taken together, their contributions are going to give a big boost in quality, and they're able to even take pre-existing models and kind of post hoc improve them with the parts that they can control, like the sampling. This is the sort of key section here. They take the problem and they formulate it in this very specific way that's then going to let them look at these different components. So we want to learn the distribution of our data, right? With a generative model, you want to be able to sample from the distribution of your data. And so with diffusion models, we're going to be continually adding Gaussian noise, right? Independent and something. It's been a while since I did any proper maths and stats, but we're adding uniform noise, Gaussian noise that's uncorrelated and so on, continually to our data. And when we add enough noise, you can't tell the difference between the data and pure noise. And so the idea is we'd like to sample from just pure noise, start with a random image, and gradually denoise it back. Oh, all right, sorry about that. Yeah, so we have these two different formulations, and often the papers that you read will focus first on the stochastic example and then the ODE. Here they kind of flip it around. And so they define, okay, a probability flow ordinary differential equation. This is just the type of one that we're looking at, where we're continuously increasing or decreasing the noise depending on which direction you're going. But it's monotonic. You're never sort of adding some noise, then removing some noise. It's always gradual denoising in one direction or gradual noising in the other. And one of the sort of components here is the noise schedule. And that's what this paper, what's one of the elements that this paper looks at as something that's worth re-examining, right? Because different formulations will just choose something that might seem slightly arbitrary even. So you have the noise schedule that corresponds to kind of normal heat diffusion, right? So physically inspired, I guess. And you'll see this parameterized in different ways. So you can parameterize this in terms of like a schedule for sigma directly, or you might have some other variable that's itself either a function of t, or maybe you just sort of scaling it linearly with t, and then deriving your sigma, your noise level from there. So you'll see various formulations of that, but they show that choosing that schedule actually has practical implications for how fast the models train and how easily you can sample from them and so on. So they're saying don't just pick this because it makes the maths easy or anything. We actually need to give some thought to this. And other works I've seen have actually taken this even a step further, like the variational diffusion models paper. Say, well, actually that should just be something that we learn, right? And so they learn a noise schedule during training. But in this case, they're just going to give some different options and kind of assess them. Okay, so that's that framing and part of it. I'm not going to go too much into the maths. We'll see some of this in code just now. Hopefully that'll make a bit of sense to it. And then the denoising score matching. So if you look in this equation here, they talk about how this delta x log p, x and sigma is the sort of score function. And they talk about, I mean, we're going to learn that, right? You could have an ideal score function, in which case you'd be able to just kind of flawlessly sample back into this distribution. We're going to try and approximate that with a neural network. And so the kind of interesting, I guess, revelation here is that we have this denoiser function, and we can either, you'll see people saying, okay, what if it's a neural network, so it's going to have some learned parameters, and it's going to predict the denoised version of X, right? That's the kind of default framing that you might think of. Given a noisy image, predict the actual image. And then we said people, well, for convenience, it's nice to have things that are not, that are sort of more smoothly distributed, maybe around zero norm. And so instead we're going to predict the noise. And the thing is, these are kind of equivalent in some ways, right? Because if you can predict the denoised image, then you can derive the noise just by subtracting the denoised image from the noisy image, and vice versa. But they say, okay, here, if we take this denoised, or this score function, right, which is going to be our learned model, we treat it as this thing that isolates the noise. We minimize the loss, saying, okay, we would like to try and predict, compare with the actual, take the mean squared error, or you can see different loss formulations in other papers. But they're saying, well, what we would like to do is kind of split this up, right? Rather than having the network try and do everything, including maybe dealing with these slightly shifting distributions and distributions that are slightly different as you are at different time steps or different noise levels, different sigma. And so that's going to be a kind of key thing that comes in to say we should be thinking about how to scale things dependent on time or number of steps or whatever your formulation, because you might have issues otherwise. And in fact, actually, we're going to do a whole set of extra preconditioning. And so they'll talk about that a little bit more, I think, just now. But with this framework, with this framing, they're able to then take some variance preserving models, like the original DDPM paper, variance exploding models, these improved diffusion papers, and a couple of other models. They can express them all in this kind of formulation, which is to say, okay, how are we solving our ordinary differential equation, right? And most of them just use Euler's method. They're going to suggest a slightly fancier way of solving that's going to help reduce the number of steps taken. How many time steps? What's our schedule? How are we determining the amount of noise, sigma? What's our scaling? And then the preconditioning is where they're going to add their, some of these just don't have any preconditioning, but they're going to add their additional scaling and transformation that's going to try and make things easier for the core sort of inner part of the network, the neural network. We're gonna condition our inputs and our outputs to try and make its job a little bit easier. And so that turns out to be quite a useful approach. Okay, and then they have some nice information on how exactly they're solving it. You can try, the nice thing with this formulation is you end up with a differential equation. You can use existing differential equation solvers, right? I've seen implementations in JAX use the excellent diffrax library and just use kind of like a black box differential equation solver. Or you can use a very simple approximation like Euler method or second order, I don't know how to pronounce this. I think a second order Runge-Kutta is also called Heun or Hyun. I only ever read this stuff. Or you can use a higher order version of that. And so they're going to show how this is sort of trade-offs with those. Some of them require more evaluations per step. And so then it's not really worth going to a super high order solver, but yeah, they think there's a nice sweet spot with a second order solver giving a better computational trade-off. Okay, so I'm trying to think whether we should jump back and forth into code or looking at the paper. I think let's just keep skimming through the paper. There's not actually too much more to go. And then we'll kind of like come back to these different sections and see, trying to practically tie it to a code implementation and some experimentation there. But one of the nice upshots of their sort of separation of these different parts, right? They have, how are we framing it, how are we scheduling our noise during training, how are we sampling, but they show that using their sampling method, right, using their second order solver and their own time schedule and so on, they can take these pre-trained models, right, these models from previous papers, and they can get to a higher quality, right, lower FID, higher quality with a lower number of, this is evaluations of the model, right? How many times are you calling the forward pass of your model? The lower the better, because you want to be as fast as possible in most cases, right? You care about sampling quickly rather than having to do thousands of evaluations just to get to a reasonable quality. And so they show that, yeah, in cases where, especially these first two examples, their re-implementation roughly follows the paper. So they're like, we're starting from a known point, but then if we add our scheduling and our scaling and so on, they can get to the solution, to a good solution much faster. And so that's what this little diagram here is showing. And that's nice. It means that we can take this method, and even if we take nothing else from this paper, kind of apply their deterministic sampling methods to other pre-trained models and see hopefully an improvement in sampling speed or sample quality for a given speed. Cool, more improvements going deeper into exactly how they do the sampling, and we can see the code version of this. Trajectory, curvature, and noise schedule. Yeah, so I think this section here, again, just to summarize, they find that choosing how you, like how many steps, what steps, how much noise you're adding, you can kind of end up with better or worse framings of that, right? And so they suggest some choices, which simplifies the equation, and they show, I think, at least an intuition of how this particular framing that they choose is going to give to like a nice stable trajectory from your noise to your final image. So yeah, I'm not going to dive too deep into that. The maths, I'm not 100% square on that yet. I should specify, not an expert in diffusion models, not an expert in maths or stats, just been trying to understand this and thought it might be helpful to take you along on the journey with me as I try and dig into this. Okay, so we mentioned that they started with the framing of the deterministic case, where we start from noise and then we're going to go from there, repeated evaluations of the model, solving the ordinary differential equation to get our output. In many cases, we want some more randomness, right, to get various outputs from a given input, or to by adding a bit of noise back at each stage, we can get maybe slightly better sample quality. And so they then in this section are just going to modify their approach to end up with a stochastic version effectively, right? So they've still got a higher order ordinary differential equation integrator, but they're adding this additional stage of like adding a bit more noise at each step. And they show that there's some trade-offs, and yeah, they're able to, I think, show kind of improvements of this compared to previous models, and varying the amount of churn, like how much extra noise they're adding, and seeing how that affects things. Okay, so the final section then, before we dive into trying to do some of this ourselves in code, or at least play with someone else's code that does this, is this preconditioning. And so they add in some nice ideas here, and these are things that have been covered in other domains, right? You've seen people doing, like, data augmentation is one of the things they talk about. That's used hugely in cases where you have smaller data sets and you're training like a GAN or a classification model. But we haven't seen too much of that yet, besides maybe just pure horizontal flips in the diffusion model case. So they have some great augmentation strategies where, actually maybe let's talk about it here. So you'll see they have this non-leaky augmentation. Let me find out where they explain that. Yeah, so what they're going to do is to say, well, sometimes we might, try and skew the image or change the saturation or change the brightness or whatever. If you can pass the parameters of that augmentation to the model and have it still try and predict the unaugmented version, then at test time you're not having to worry about it generating skewed images. You're still learning the true data distribution, but you're reducing your chances of overfitting. And so that's a nice, neat little extra step there. But even without that, the nice thing with this paper, all of these improvements are kind of additive. But the other sort of key things here, one of them is, like I said, the preconditioning, which you'll see just adding some time-dependent scaling and choosing how much the outputs of the network are going to focus on different components of the loss, right? So you have your loss function here of your inner network, and it's determined by these extra parameters, C in, C out, C noise, etc. And so those are parameters that we can set. And this is effectively saying, rather than having the network try and learn these as part of learning everything else, we're going to kind of surround it with a wrapper that's going to do this preconditioning and then post-processing, if you will. So that's one sort of neat extra thing. Then the final part here that I thought was really interesting, actually, and one of the most sort of intuitive but also useful applications or outcomes from this paper, is to say that if we're considering this case where we're adding noise according to some schedule, and we can look at the diagrams here, if the model is seeing an image that has virtually no noise added and it's trying to predict the image itself, right, that's, you can think of as potentially an easier task. It's just predicting a very small amount of noise, or maybe at that stage you just can't really tell whether there's any noise or not because it's indistinguishable from the natural noise in most images. So at those very, very low levels of noise, there's not much useful we can learn, right? And then as you go more and more noise, now it's you can still see maybe overall structures, but there is a lot of noise that you have to predict. So that initially a model might do really badly, but over time it could get better, right? There's room for improvement there. But then if we think of, as we're training, we're taking a known image, we're noising it, and we're trying to predict the noise. If we noise it too far, it's indistinguishable from Gaussian noise. And so the network can't really do much with that. And so you can see that over here, as we increase this, the noise level is on the x-axis, and it's a logarithmic axis. The really, really high noise region, the model hasn't really learnt much, right? It's still, the distribution of the loss looks pretty much like it did after initialization, right? And at the very, very low level, we've learnt a little bit, but it's not much of an improvement. Whereas in the center here, that's the kind of key region. And so they choose, during training, they choose to create more samples in this region, right? So the network's going to see a lot more examples in this useful region where it can actually learn things, and a lot less on the outskirts. And so, yeah, that's a really nice, clever, obvious in hindsight insight, which is exactly the kind of insight you want to get from a paper, to say, oh, yeah, that makes sense. And so we'll see this in the code. And that means that you're not wasting a lot of time on samples that aren't really teaching your model as much. And so really great little improvement there. Okay, so I think that's enough for a first skim of the paper. We can come back and look at individual sections. They also have a number of appendices going into how they take previous methods and fit them into their implementation, right? You might have seen previous ones specified by, a schedule for beta, and then alpha is derived from that, sigma or whatever. So they have lots of ones there. They have further analysis of some of the things that they talk about, further results, implementation details. But for now, we're going to instead look at an implementation that's currently in progress, very much a work in progress, but we'll then also use that to try and train a diffusion model. Excuse me. Okay, so this is the notebook that I have here. Let me just restart the runtime to clear everything. I will share this in the link in the video if you want to follow along, but this is not like a full notebook. This is just effectively a scratch pad to get things going. And the implementation that we're going to be relying on here is by Catherine Crossan, an amazing sort of member of the open source community who's been working on creating their implementation of this paper, right? This Karras et al. Elucidating the design space of diffusion-based models. So we're going to be relying on a lot of that code, and we're going to be playing around trying to generate, in this case, some celebrity faces, right? This is the Celeb faces dataset from Hugging Face. Okay, so we're going to work at a fairly small scale. Everything is just for demo here, but we set it up so that in each batch we're going to have 16 images, 3 channels, 64 by 64 pixels. So the first component that I want to talk about is the noise schedule. And you'll remember that I said, past ones have done maybe like just a linear noise scale. And so you're continually adding more and more noise so that the original image is less and less distinguishable until after, some large number of steps, you can't even, it's sort of equivalent to just pure Gaussian noise. And so we can see something like that here. But remember we said we'd like to focus on the sort of interesting region where the model actually has a chance to learn something useful and to reduce the loss. And we'd like to see less kind of extreme cases on the far end and less almost zero cases on the other. But mostly we're more interested in the front end of this section. And so if we now take their, they said they use a log normal distribution. I just thought it'd be nice to kind of plot out what that looks like. In the paper, right, they show it with the log axis. So it's this nice smooth distribution. You can set the mean and the standard deviation. But in this case, we can also just draw some samples from that distribution and show how they are spread out. And so you can see here we have most of our samples centered at fairly small amounts of noise, but this long tail, right? I think the maximum value in this particular example was 62. So we are going to occasionally get some really high, super noisy images, but they're going to be kind of skewed to be more in this interesting kind of earlier section, but also none that are completely, zero. Okay, so that gives us a distribution that we can draw from, and so you'll see during training that's exactly what we're going to do. We're going to take a batch of images, we're going to then combine them with noise, and the noise scale, the sigma, is going to be drawn from this log normal distribution. And so then we'll get a batch of images, different each time. I'm not going to use a single face, don't worry, but we'll see different amounts of noise, and you can tweak the mean and standard deviation if you'd like to experiment with that. Okay, so then the next part is the actual modeling, right? We said we'd like to learn this denoising function that takes in, depending on how you frame it, your noisy input and some time step, or in our case, we're just going to condition it on the amount of noise directly, and it's going to try and predict the actual noise itself or predict a denoised image. And so in this implementation and in the paper, it's going to be based around a sort of UNet architecture, right? And so you can see this is our base sort of UNet class, a number of down blocks, a number of up blocks with some skip connections. And then it's going to be wrapped in this image denoiser model. And this is going to set up some extra things. We want to condition on our time step or our noise, right? So we're going to set up some Fourier features based on that, and then a mapping. We're going to just set up some sort of initial and final layers, and then our forward pass is going to take our conditioning, embed it, and then run this sort of projection in, then our unit, then our projection out. And so you can think of this, the unit itself, right, the raw neural network being that f, let me find it in the paper. Yeah, this f theta, right, this learned set of parameters, this is our internal thing. And then you can think of the outer model being the extra conditioning. And so we can see, oh yeah, and actually this is not that. This whole thing is our raw network, right? And so we can create a version of this type of model, and we can see, if you comment it out, this is just a PyTorch model with all those layers populated, and so you can go and skim through and see those, and we can pass in noisy input and sigma and see that the output is the same shape as our input, right? Our demo here had 8 images, just those 8 repeats of the same face. And now we'd like to wrap that in that extra conditioning, and so we're going to use layers.denoiser. And if you go and read the code, this will be in Diffusion layers, you'll see that this is just adding that extra C skip, C out, C in. This is doing that extra preconditioning and so on. This is like the wrapper around this inner model. And so it does the same sort of operation. It's just that now that we've wrapped it in the denoiser, the sort of outer model, if you will, the preconditioner, this is now going to rescale our inputs and make it easier for the inner model to learn. That's at least the theory. And that class also provides some convenience functions like the built-in loss function, right? So we pass in our noised input, the actual noise, the known noise, and the sigma, and then we get out a loss for each image. And so if we wanted to, during training, we'll take the loss.mean. And that's going to be our loss function that we try and optimize. So with that sort of setup done, we can see what an example training loop might look like. We're going to set up our inner model and then our sort of final model with that wrapper. We can specify, we're working with RGB images, but if you're doing latent diffusion, you might have a different number of input channels. Specify the depths of each unit block, the number of channels in and out, and whether or not to have self-attention. Right? Most of the unit implementations in these diffusion papers have some sort of self-attention at the lower levels. And then you can, if you want to be fixed to a specific resolution, you can also add cross-attention, although I see that less these days. Okay, and so then we're just going to set up some logging, set up a demo function, which we'll talk about once we talk about sampling. And then just running through the data, right? For every batch, we're going to get our real images. We're going to generate some noise. We're going to pick some sigmas, right, some noise levels from our log normal distribution, and then we're going to calculate our loss, right? Pass in our real images, have the model noise them according to sigma, try and predict that, calculate the loss that backwards, update our model's parameters, right? Optimizer here just takes in the parameters of the inner model, the outer one, the scaling and preconditioning and so on, no learnable parameters there. And then we've got a learning rate schedule just to kind of improve training stability and so on. Some logging, saving some demo images every few steps. And so you can go, I'll make sure that this project is public, so you can go and check out the results. And if you look at the demo images, you can see the loss goes on over time, right? We're just doing a single epoch. This took about, I think, 40 minutes. So it's not going to be the best diffusion model ever. The existing ones are trained for a lot longer. But it does work a lot better than, say, my previous experiments with the original DDPM paper framing. Took a lot longer to get coherent outputs here. After, at 0 steps, not much. After, 500 or 1,000 steps, you start to see a little bit of structure emerging. And then not that much later, you begin to see some images that actually do look at least a little bit like celebrity faces. Well, perfectly normal human beings right there. So yeah, you're welcome to go and play around and view some of these outputs. And it's quite fun to see. Obviously, if you ran this for longer, maybe used a slightly larger network, more channels, more parameters, you might actually be able to get fairly quickly some pretty decent looking results. In this case, the model has just 18 million parameters, I think. So quite a small model as they go. How big is the file? Yeah, 70 megabytes if you want to save the weights. But you are highly encouraged to try some larger models and see where that takes you. So because I've restarted the notebook, I'm just going to reload that model. I've saved the state dict. And we can talk about the final section, which is the sampling. And so In the paper, there's a couple of things that they do, right? They use their second order solution or solver. They have their sort of sigma schedule, their noise schedule, and both of those things together mean that with relatively few steps, they can get a pretty decent output. So the first thing I wanted to examine and to check that the code was working right. So this is our noise schedule. We're going to start with a fairly high value of sigma, and then it's going to drop off as we get closer and closer to our final output. We're going to end up very, very close to 0. And if you want to go and see the function for that and tweak the parameters, that is in the sampling file here. There you go. And then you can also see, so this is figuring out their noise schedule. You can also see their the implementations of the sampling methods, which I think they cover in maybe the implementation details of the paper. I'm not sure, I'm not going to try and find it now. But anyway, so with that noise schedule and then the actual sampling function, we can take our trained model and we can just start from random noise, right? Let's start with 16 random images. And then we can tweak the number of steps. So let's see if we use a lower number of steps, is that going to be better or worse? And so yeah, you can go and play around and see the trade-offs, see that maybe the images are less diverse or more warped as you go fewer and fewer evaluation steps. But it is quite fun to see that even with a relatively small number, you can get some coherent outputs. So really, really nice sampling method. And like I said, you could take just this part of the code and apply it to a pre-trained model that had been trained in a slightly different way. So I think that's going to be very useful even outside of models that are trained with their training noise schedule, that log norm distribution, and so on. Cool. So there we go. We have a diffusion model trained in, what, half an hour, 40 minutes, explained in half an hour or 40 minutes. And with a relatively small number of steps, we can get some almost realistic outputs. I know celebrities that look just like that. And with a bit more training and a slightly larger network, I'm sure you could get even better results. And like they show in the paper, if you're willing to wait for a long time and put in some more effort training, you can get state-of-the-art generation with this, right? Beat all the past methods. So really, really nice paper, really nice method. And I think it's great that we're starting to see approaches like this that take, these confusing topics with lots of different kind of angles and views, and are trying to say, let's approach this systematically. Let's break this down into different problems. And I can see the influence of this even if you look at like the Hugging Face diffusers implementation that's just starting to be worked on. People are trying to build things in this modular way where we separate our training schedule from our sampling, from our actual model implementation. We're not stuck with this particular UNet implementation or this particular preconditioning or this particular augmentation. We're just able to kind of mix and match these different components and have reasonable discussions about the pros and cons of each of these kind of individually. So I hope you've enjoyed that. A different type of video for me. I think I've been missing making videos since the course ended. So let me know if you'd like to see more explorations like this. Like I said, this is just me trying to get to grips with the topic myself. So I'm by no means an expert. I've probably missed some points or made a few mistakes, but if you spot any, let me know and we'll put corrections in the comments. For now, thank you so much for watching. And yeah, we'll see you next time here on Data Science CastNet.